All right, so today is about something called locality-sensitive hashing. It's going to build on our last lecture, uh, which was about this dimensionality reduction stuff. So this is also a big data topic. Let's see. Right, what we did last time was this idea that you can take high dimensional data, and if you only want to preserve distances or dot products or something like this, then you can actually project it down to just log n dimensions. So you can start with arbitrarily large dimensions, you can get that down to log n and roughly preserve all the distances, which is often all you actually need if you're going to cluster, if you're going to do regression, whatever. Okay. And, and really it was just a matter of understanding Gaussian random variables. Just knowing that sums of Gaussians are Gaussians and that high dimensional Gaussian vectors, the length is extremely well concentrated. Those are the two things you need to prove this result. Okay, so that was pretty exciting. Today, our application is something called approximate nearest neighbors. I'll introduce that in a moment. And sort of an interesting approach to it called locality-sensitive hashing. So, okay. So nearest neighbor search is exactly what it sounds like. You have some points in some geometric space, and you have some query point, and you want to find the closest point. Okay, so it's like a retrieval thing. Like Google image search retrieval, right? You give it an image, it returns similar image, things like this. Um, so this is used quite a lot. You have a search query, you look for similar documents, things like this. Okay. Uh, so today we'll talk about, you can have two different, or you can have many different, geometries depending on the application. So today we'll look at two of them. One, maybe not so surprising, is Euclidean distance. Okay, so you want to find the closest Euclidean distance points, or approximately. And the other one we'll look at today is the angle, right? So it often makes more sense if the points are already like on the high dimensional sphere, so they have unit length, and you want to know which close points have small angle, far points have large angle. So, so that's what we'll try to do. So okay, oh, is this the wrong version? Well, okay. I was going to ask you, what would you do in one dimension? Okay, so a really simple version of the problem, or the simplest probably, is where you have the points on a line, right? And you're just like here, and you want to know what's the closest points. And of course, you do something like binary search. You can sort the points first and binary search for it. Or if you want it to be a data structure where you add and remove points over time, you'd have some kind of tree, right? So, okay, sorry to spoil that, but I think it's maybe not that interesting a question anyway. This also works in high dimensions. Okay, so you can take the binary tree idea and do it in 2 dimensions, 3 dimensions, 4 dimensions. But does anyone know what the running time is? How it scales with the dimensions? Yeah, so usually most of them is going to be something like log to the kn. So 1 dimension is log n, 2 dimensions is log square n. Sometimes there's some tricks where you can do log to the k minus 1n, but the point is like as soon as k is like 10, you're screwed, right? So it's not going to help you with some of these modern settings. So that's really the main thing we're trying to overcome. We want to do something that's basically trivial in low dimensions, and the real crux of the problem is how to do high dimensional searching. Okay. So yeah, maybe I don't know. It's more fun to give you guys a chance to guess an approach. I guess you know the name of the lecture, but you don't know what it's about, so you still have to describe something. How might you try to go about this kind of problem if things like quad trees and range trees are out of the question because the dimension is too high? Yeah, I can project to a lower dimensional. We can try to use the techniques from last time, right? So based on last time, we can project to what dimension? Log n. So log n dimension is enough, but if I plug in log n here, log to the log n is not that great, right? So if I have a million points, then suddenly k is 20. So I don't want to really do log n to the 20. It'll be 20 to the 20, I guess, right? For 4 million. Okay. But that is a very natural idea. Why don't I just project down to log n? But somehow the dimension is still a little bit too high because it's exponential in the dimension. So we're going to eventually allow for approximations. So I think the actual form, for example, can you find a neighbor that's within a factor 2 of the nearest neighbor? So something like that, yeah. Let's say for Euclidean distance, for the sake of concreteness. You can pick any distance you want, really. Okay, so it's not clear what you can do in high dimensions, right? So from that frame, let me suggest. Suppose I told you that maybe there's an approach based on hashing. How might you use hashing to solve this problem, or what would you want your hash function to do? Yeah, yeah, that would be great. So usually when we do hashing, right? We want, like when we do dictionaries, we want these items to be like spread out, right? We don't want collisions normally, right? So we usually try to get like very, very random hash functions that in principle should lead to less collisions. Like this is what we wanted before, was no collisions, right? But in this application, if we can get the nearby points to actually collide with, slightly non-zero frequency, something like this or something, right? Uh, which is, not perfect, but there's some correlation between, where it is geometrically and where it gets hashed into. Okay, now then maybe something could work, right? So that's the idea we're going to explore. It's sort of a very creative idea. Can we come up with something like hashing, except it's actually trying to increase collisions? Collisions are a good thing for us. And if I can get nearest neighbors to collide, then maybe I can just scan this bucket. And, then maybe there'll be some things that aren't near neighbors, but hopefully a near neighbor will be in that bucket, and that bucket won't be too big. And you can just scan and find it. Okay, so that's the approach we're going to take. It's called locality-sensitive hashing. And this turns out to be extremely practical. Like, yeah, like basically every web company, like underneath the hood, is just doing locality-sensitive, like for everything. Like they have one person there who's like the boss of local, and that's his job. And yeah, this is insanely useful. Okay, so okay, so all right, so we'll start with Angular LSH. Now the input really looks like this. Actually, it doesn't even look like this, but the input is on a high dimensional sphere, which is extremely hard to visualize. On the surface of a high dimensional, well, we're just doing angles, so I can assume everything is normalized. It's only the angle that matters. But the real thing is that it's on some high dimensional sphere. Okay, and I have some query point. I want to find the closest point in this high dimensional way. It is true that if you kind of look at any slice, kind of two-dimensional slide, that's a two-dimensional picture, but it's a little bit misleading is all I wanted to suggest. Okay, so the goal is to build an LSH scheme over this, for this. Okay, so I'm trying to come up with some kind of hash function, some way to assign it into buckets or something that hopefully Helps things collide that are close by. It might be even helpful just to try to think of something that works in 2D. Sure. So some level, can I try binary searching like this, like this, like this? Okay, so what I think what this is effectively doing is it's projecting onto this line, and then it's doing binary search. Now, one tough part is that to project onto the line, you have to go through all those points and project it onto the line, right? So you want to build a data structure over this so that you can do this fast. Your algorithm will work, but I think just, taking every point and because you're rotating the system, right? Yeah, but rotating is going to require touching all the points, at least if you're going to explicitly update their coordinates. We're trying to do something that's like a hash table. Just go there and you're done-ish. Yeah, so the dot product is a projection onto it if the vector is already normalized. Yeah. So yeah, minimum distance is maximum projection. That's true. But the issue is more algorithmic. How can I do something fast? It doesn't have to be right all the time, and it doesn't have to be exact, right? But is there some way of kind of randomly assigning things that would be kind of correlated? Yeah. Okay. So first of all, you in 2D, you can actually imagine building something like a binary tree over this. This is sort of like the low dimensional ideas. And this is sort of like combining neighboring buckets at some level, right? You can try to do things like this. I think you're going to run into the same issues we had before. This isn't quite correct, but so so ultimately to do things in high dimensions, you're really if you're just working on the sphere and treating the surface of the sphere as like a one-dimensional less space, you're just building a KD tree over a basically a D minus one dimensional space, which is still high dimension. Yeah. What's a reasonable way to try to say split the data set in half, roughly half? Huh? Draw a line somewhere. Where should I draw the line? Okay, you can draw it vertically down the middle, and then of course, if the two neighbors are, okay, so you want to split the line, split it vertically, right? But if you're, obviously the adversary is just going to put the nearest neighbors right near the line, yeah. Oh, okay, I can try, right? Something like this, and seeing where it lies, right? On which side of the line. If they're nearby neighbors, if they're really, really close, you would have to, there's only a small angle in which you can get unlucky. And it'll at least be correlated, right? Now, that'll only split it in half. And so, which case you'll, do a hash table and you have to read a list about half the size. So it's still a little bit slow. But if I wanted to take this idea further, yeah, we can generate more lines. Now I really like this animation, so I can't help it, right? So, you sample another line like this, right? And so you can sample a bunch where each line you sample generates one more bit of some kind of like hash code, right? So if I do it 10 times, then roughly all the bucket sizes should be like n over 2 to the 10 on average, because each one should cut it in half on average, right? And then and then you can at least see some correlation. Nearby points are much less likely to get split up than further points. That's a reasonable idea. How do I generalize this to high dimensions so that I can draw a spinning circle when it's on a plane? So how do you implement exactly the exact same idea in high dimensions? Oh, well, first of all, there's two dimensions here. So are you trying to pair? Oh, well, yeah, in this picture, that's not actually what we're doing, right? Because there's two dimensions here and we're treating them jointly. Yeah, yeah. Okay, so one option is to try to treat the coordinates differently, but do something for each coordinate. Um, yeah, so a line compared to two dimensions is really a hyperplane. It's like, d minus one. The way to generate a random split, a random hyperplane is, I don't know if I can draw this as well, but you 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 choose a random direction, okay? And then you project all the points onto this direction. Uh, so I'm kind of going to get taken away with drawing pictures, and some of them are going to have a positive projection onto it, and others like these will have a negative projection. And I suspect that drawing any picture is actually misleading as to what's actually going on in high dimensions, but so this is more like a metaphor or something. Okay, so really the split is going to be like more in this direction between the points with positive and negative projection onto the yellow. So you pick a random normal vector to the hyperplane would be the terminology. Okay, but you pick a random vector on the sphere and you compute the dot product, you see what's positive, you see what's negative, and that's how you split a high dimensional space in half. Okay, so that is the idea, and we are going to focus on the following parameterized thing. Okay, so instead of like the nearest neighbor, I'm going to just focus on like close neighbor for some parameter of close. So I'm going to give you some parameter theta, okay? And your goal is to either output a point with angle at most 4 theta. I'm not sure why it's 4. I thought it was going to be 2. Doesn't matter. Some constant times theta. Maybe 4 is just easier in lecture. Or declare there's no points with angle less than theta. So there's some margin of error, right? Maybe there's no points of a thing less than theta, but you return something with 2 theta. So there's some error there, which will, make life a little bit more plausible. If you didn't allow for any error, then because theta might be really close to some boundary, you'd have to compare every pair and you're kind of screwed. So we're going to allow for some error and focus on this parameterized regime. Okay. Now, if you can solve this problem, then how would you get an approximate nearest neighbor? So for a particular theta, you can get this within 4 or not. If you had something that can do this really well, how would you actually get an approximate nearest neighbor? Like something within a factor 4 of the true one. Yeah. Oh, yeah. Just binary search, right? Choose a big theta to start with. You'll find at least one point. Okay, the true distance is something smaller. Divide by 2. See what happens there. So you can binary search and actually get an approximate nearest neighbor with some logarithmic overhead. Okay, so it suffices to work on just this version of the problem where it's a little bit cleaner, and then the rest comes kind of very easily. So that's I'll focus on this regime. Um, okay, so so you all know the algorithm, and so I didn't really explain it algebraically, but basically it suffices. I mean, one way to generate a random direction is to sample a random Gaussian. Okay, so if every coordinate is Gaussian, because Gaussians are rotationally invariant, if you rotate the space, you still get a Gaussian vector, which I guess I never said before, but this will be important. Okay, um, it's still a Gaussian vector, so that'll be kind of analytically very convenient. Okay, um, so here's the claim. So our algorithm ultimately is going to sample G, where every coordinate is Gaussian. And then you're just going to compute the dot product gx and gy for all these points x and y and see if it's positive or negative. And the sign is going to tell you if for that round they got the same hash code, right? So that's the algorithm just presented analytically. Okay, so the claim is that the probability that x and y get split up, the probability that the signs of the dot products are different, is their angle divided by pi. Question is why and how to see this. Yeah. Okay, so if it was at least in 2 dimensions, okay, if it was at least in 2 dimensions, then as we discussed, this is some random line like this. So if this was x and this was y, right, and I drew lines through, sorry, my x and y look the exact same, right? So in 2 dimensions, I did it again. Okay, in 2 dimensions, right? So in 2 dimensions, there's 2 pi total choices. And, if I'm in this sliver or the opposite sliver, that's the only time they get split. No. Yes. Uh, it looks like the probability that they're equal, right? Oh, okay. So it depends on. Oh, right. Yeah, yeah. So, okay, there has to be a. Okay, I think I know how to do this actually. One sec. You guys are gonna be amazed. Okay, I'm gonna draw a perpendicular line, and then. Oh wait, sorry. As usual, I'm just drawing pictures instead of teaching. Okay. All right. So the yellow line is what we're sampling, and it's going to split at the purple line. Actually, I should have drawn the purple line all the way across. and I regret not doing that. So if I rotate it like this, the purple line splits it, okay? So in order to get the purple line in between, okay, and this is actually splitting the points at the purple. So you sample the yellow and you split at the purple. It's actually in, okay. This doesn't quite. So, okay, but you get the point, right? So there's actually only this margin of perpendicular lines to these rays for x and that's not how you do it. So this would be like one perpendicular line to the x line, and another perpendicular line to the y. That's not quite perpendicular. Something like this, right? And it's only when it's between the two normal lines, okay, that it gets split up. Okay, so this is in fact the angle, the probability that it gets split up in 2 dimensions, right? So how do I go from many dimensions to 2? Yeah. Yeah, so if I'm only looking at 2 points, I can look at the plane induced by the origin x and y. Then I have a picture that looks like this. And I can rotate the space to be convenient. If you rotate a Gaussian vector, you get a Gaussian vector, so everything is fine and our 2-dimensional argument is fine. All right, so this is all about Gaussians being the nicest variables in the world. Anything you want, you get for free. Okay, so that will be our algorithm. So we'll do it k times, or some k that we'll decide is appropriate. We'll figure out like the best choice. Okay, and see what's written here. Okay, so the algorithm is, we make one of these hash codes, which is doing k of these random splits, and then I'm going to group the point set by hash code. So it's like a table, right? And it just lists all the points with the same hash code. And then now, if I want to query a point y, what would I do? Yeah, okay, so you just scan all the points with the same hash code. So that's the algorithm. The algorithm itself is extremely simple. At the very least, this is much easier than making a binary tree kind of thing, right? Like if you're just lazy, you would do it this way. Yeah. Yeah, okay, so what's going on? Yeah, so what happens if points are really clustered? Yeah, so I think this is where we're going to leverage the fact that we're only doing approximate nearest neighbors. Yeah, so doing exact things starts to get really, if you're not careful, if you're doing exact problems, then you might find that you have to check all the points or you're just not sure. And then you're screwed anyway. So this is another one of those like, oh, I want to do something practical. So I'm going to do a trade-off. And I think in general, this seems to work out pretty well because our data is already noisy and the representation is a little bit arbitrary, right? So yeah, it just seems to work out okay. I think often it seems like what you're really interested in practice is that you have some points that are actually really close. And then most of the points are just super far away and useless, right? You're really looking for a picture of a bike and that only represents a 0.00001% of the data set. So most of the points are really far away. You're going to filter out most of them and you're going to return a picture of a bike, maybe not the best bike. And then probably you're going to return a bunch of them and then let the user choose. And, there's other stuff going on. So somehow it seems like this trade-off is still very good in practice. Yeah. No, we searched the bucket and we should return the best one you find in the bucket. And if you don't find anything in the bucket, maybe you should try again. Try another hash, right? So we might find that this hasn't come up yet, but there's going to end up being 2 dimensions. One is, what should I make k, right? How many bits do I need for a certain runtime? But even then, the algorithm might fail to find anything even when it should have. You could have just got really unlucky. So we might even take this scheme and repeat it after that. So there's 2 levels of repeating. One is to just repeat within a hash code to make one hash code. So that's like an and then you're going to repeat that construction several times and take like the best of. It's like an or. Yeah. Yeah. So what's the basic trade-off? The trade-off is that the higher k is, the more likely you're going to kill off the nearest neighbor. But what's the good part of increasing k? It's faster because you're decreasing the size. So we need to figure out like what's a good trade-off. We need to do the calculations, figure out the math, and see what's appropriate. Yeah. Good. You guys are asking all the right questions. Okay, so okay, so okay, I think what we're supposed to do here. Okay, so let's say I have 2 points x and y, um, and their angle is at most theta. You guys think of it as equal theta because that's the worst case. We want them to stay in the same bucket, right? So we should try to calculate what is the probability that they are in the same bucket. So what's the probability that hx is equal to hy if their angle is, if they're near neighbors, right? These are the ones we want to be together. You can do less than equal if you want. So as a function of k, right? Okay. Uh, good. Want to make sure. Okay, so now consider the case. Well, let me come back to it. Okay. Uh, okay. And then what happens if the angle is greater than 2 pi? Well, okay, it's going to be the same thing, right? So here I don't want them to collide, right? But what are the odds they collide? It's going to be 1 minus the angle again. So I think the earlier 4 was supposed to be 2. That's what it is in the notes. To the k, and this is at most e to the negative the angle between them divided by pi times k, right? And the angle is at least 2 theta. Okay. Now, okay, this next part I'm going to cheat a little bit to keep the calculations a little bit cleaner. So bear with me. So in the regime where the angle is pretty small, like really much smaller than pi, then 1 minus x is basically e to the minus x, right? It's going to be actually greater than e to the minus x plus x squared, for example. You give back a second order term, but x squared will be small if the angle is small. And I kind of don't want to carry those calculations with me for the sake of this lecture. So let me cheat and just say, okay, this thing is about, we can go back if you're curious and do the calculations more carefully and put that second order term back in. Okay, but let's at least see how the first order terms make sense. So if the first order approximation, this is true. Okay, I could have added plus angle squared over pi squared over times k. So if this is like at most 0.1, you're only giving up 0.1 or something, right? Okay, so that's fine. And now if I compare, uh, right, okay, so let's look at these two things, right? Is this a good view? Okay, so what might be a good choice? Okay, so this now we're at this question of how do I choose k? right? So it is true that it's going down exponentially fast in k, which is not great, right? But oh, and let me plug in theta. Uh, so let me write this is greater than or equal to e to the negative theta over pi k, and then that's less than or equal to e to the negative 2 theta over pi k. Okay, so that means that, for example, the probability that you find a good point, right? The probability of success is about e to the minus theta over pi k, which means that if I want to get to like a constant probability of success, how many times, let's say I chose k, right? So there's this limited probability of success. And I want to say repeat the data structure enough uh, so that I have a constant probability, for example, of success. You can multiply it by log n more to get high probability. So roughly how many times would I want to repeat the data structure for a fixed value of k to guarantee a constant probability? Sorry? Yeah, 1 over. So if you have a coin that like flips heads 100 times, yeah, you need like 100 coin tosses to get it up to a constant. Okay, up to a constant. So so this implies, you might need to repeat e to the theta over pi k times, right? Whatever you choose. And okay. Now, on the other hand, um, when you go to your bucket in a particular run, you're going to see a lot of noise, right? So your running time is basically like you're going to hash, and then you're going to spend time proportional to how many other points you have to actually carefully look at within the same bucket. Okay. So what is the expected running time of just one of these copies for one hash code, that is? So I hash it, I compare it to all the points in the same bucket. So really, how many points do I expect? Sorry? 1/2 to the k? Well, that's sort of similar. So we already have this expression. Okay, what I meant to say is that so the expected time of each one of these runs is going to be n times e to the negative 2 theta over pi k, because each of the other points is going to collide with you and waste your time. It's probably e to the negative 2 pi over k or something, right? So, okay. So those are like our basic trade-offs. What's a reasonable choice of k? My real goal, let's say my goal is to beat n squared. Or no, my goal is to beat n. Yeah. So what if I said, okay, yeah, what if, or what are some reasonable choices of k? We just want to plug in some k's and get reasonable running times, right? Yeah? Okay, what if I did k is equal to log n, then we get n times uh, n to the negative 2 theta over k, over pi, sorry. Okay, so this number is slightly less than n, but of course theta is really small, it's very close to n. How can I, 2 log n? Okay, it'll be to the negative 4 theta over pi. So again, if theta is really small, you'll be very close to n. We just want to cancel out the theta, right? So, okay, what should I put in front of the, oh, sorry. So maybe I'll put some coefficient in front. Pi over theta. So that will get me, this will cancel out. N to the minus 2. Did I do that right? Oh, there's a, yeah, I think I did that right. That's a bit weird. So you get 1 over n in expectation. If k is pi over theta log n, uh, okay, so if you did k equals pi over theta, now what are the odds that you succeed? Which is going to be e to the negative log n. So this is when we're choosing k to be pi over theta times log n. So you get 1 over n chance of success. Okay, so now we'll have to repeat n times. So that's not great. Okay, so we're getting closer, but k equals pi over theta log n wasn't quite good enough. You're also seeing on average, yeah, places C everywhere. Yeah, so give me a nice C. Give me a nice C that's a number. Can't say no to a lecture. It's like breaks. Once you start doing that, like the prisoners, inmates run the asylum. Um, which maybe it already does. Anyway, just give me a better choice. Like this was just like a little bit too aggressive, right? All right, let's try 2. See what 2 comes up with. Uh, so you expect to see like one bad point or something, right? So that's not bad as far as noise goes. So you waste a little bit of time looking at noise. Now, what are the odds of finding a good neighbor? State Farm is there. Okay. So now there's a 1/2, right? So you're going to get log n over 2. So you get 1 over square root n, right? So you get 1 over square root n probability of success, and you spend constant time looking at noise. So you repeat square root n times, right? And then you get constant probability of success. You repeat square root n log n times, and now with high probability, you'll find a near neighbor if it's there, right? So overall, if you include all the repetitions and we choose k appropriately, the overall running time is like square root n log n kind of thing. Maybe another log n because you have to compute log n hash codes or something. But it's roughly square root n. So you're not looking at almost all the points. Like square root n, when n is big, is represents 0% of the data set, right? As n gets bigger. So you're looking at a very little of the data set, and you're going to find an approximate nearest neighbor. So this is fantastic, right? So people, for example, explore ideas like, you guys know how LLMs work? People have tried using this for the attention step, which is a bottleneck and so forth. But this is which is sort of an obvious idea. But anyhow, you can start to see, okay, why this is really appealing. Super simple algorithm, right? Sublinear time. And this is even like assuming the worst case where like all the other points are exactly distance 2 theta away and you only have 1 point at distance theta or something, right? If there's actually better, more natural spread, then you're going to get better bounds than this. So it seems like in practice, like people just treat this as super solid. Just throw LSH at it is what I kind of see. So this is very practical. Yeah. Yeah. Well, the question just doesn't isn't too concerned with clustering. If there's many points, that sort of makes it easy for us to find one of them. So I think what I would do is I know theta, right? So as I scan the buckets, as soon as I find one point within distance theta, I just return it. Yeah. So what we'll do next time, since we've spent today's time, next time we'll look at the Euclidean case. We'll do something different, a different algorithm, but we want to do the same principle. I want to come up with a hash code so that the nearby points are more likely to hash in. Okay, so our goal next time will be to come up with an LSH for Euclidean distance. Yeah, so that's what we'll do next. And then there's people who look at, you'll have a homework problem on Hamming distance. It's like number of bits that are different. Um, and then people, yeah, probably look at lots of things. And then people also do a lot of heuristics on top of this too, just engineering things that seem to kind of work sometimes. Like, um, yeah, I don't know. People are been recently excited because they programmed this to run on a GPU, which I don't know. It seems like kind of straightforward, uh, but obviously the GPU would just do all the dot products at once and stuff, right? Sometimes people like to do clustering first and then throw it into LSH, like a little bit of light clustering, to try to take advantage of clumps of data. I've seen that. I don't know if there's very clean characterization of what you get from it, but in practice, people find this helpful. Yeah. Other comment. We covered the material because there's no time to start the next thing. So, any other questions? Yeah. Yeah. Well, you can terminate. Well, until you get. Well, you might get bad point, bad point, bad point. You don't know if there's a good point, right? Oh, okay. So there's an outer binary search for the best data. And then on the inside, what happens if there's many good neighbors and you only need one of them? You should just stop as soon as you find one. So basically, once you find a theta where you don't find a near neighbor, with high probability that theta is too small. Now you have to start getting bigger again, or from your direction, bigger again. Yeah, yeah. Go bigger, smaller, bigger, smaller. So until you're happy, right? Ah, it's close enough. Yeah. Okay, that's it. I'll see you guys Friday. Okay, so let me just remind us where we left off. All right. So we're talking about this approximate nearest neighbor problem. So the high level thing is, okay, you have some points in high dimensional space and, get me the nearest point or say something within a factor two of the nearest point. And we're looking at two different distances. There's a whole family of, work on this for different distances. We did angle last time. Today we'll do Euclidean distance. On the homework, you'll do Hamming distance. Uh, you know, this is just pointing out it's kind of easy in low dimensions. The challenge is high dimensions. And so the interesting, conceptual idea is that we're going to try to invent some kind of hash function where collisions are actually more likely for vertices that are closer together than far apart. Okay, that's the high level idea. How you would actually ultimately use this in an algorithm is that you build some kind of table by hashing in, and then when you have some query point, you'll hash into the slot and see, scan that list. What's the closest point? Okay, and that's your guess. Whether it's right or wrong depends on the analysis. And what we found is for angular stuff, ultimately, okay, so we're doing this thing where we choose a random angle. And not only do we actually choose a random angle once, but we ended up like repeating this I guess this looks a little chaotic, but we'll actually repeat this random hyperplane many times, right? Each hyperplane will give us one bit. So if I do 10, I'll get like a 10-bit hash code, and that'll be the name of the bucket. The reason I wanted more bits was because it filters out with greater probability the things that aren't points we're looking for. But of course, every time you add a bit, you might also kill off and split off the point you are looking for. So to repair that, we take our 10-bit hash code or something, and we'll repeat that several times. Okay, no, I think ultimately, I don't actually remember. I guess we repeated e to the theta over pi k times. Okay, the number of times we repeated was actually slightly a function of this theta we were looking for. So if it's very small theta, we would repeat less and otherwise repeat more. I guess it should probably, no. We should probably repeat about square root n times, right? Because we chose k so that it succeeds with probability 1 over square root n. So we end up repeating the 10-bit hash code about square root n times. So you build square root n tables, and now given a query point for each of your tables, you'll just hash in and search the list and see if you find something close to this target value of theta. If you do find something, you can just end the search right away. And if you don't, yeah. We also talked about, okay, you only expect to get one bad point or so in each of these tables. So the running time shouldn't be too bad going through the useless points. Okay. That was for a fixed parameter theta. I'm really looking for things, I don't know, within angle 0.01 or something. So we would do this for different values of theta. And then you can binary search and things like this. Okay. So that's the idea. We're kind of, ultimately it kind of looks like a hash table, but the characteristics are different because we want things to collide if they're nearby. Okay, but otherwise the performance has all the benefits of, like a real hash table or something. Like it's really simple, it's really fast, it seems to work really well in practice, things like this. Yeah. Yeah, so I think at the end of the day, because you need to see, is it written here? So we're repeating about square root n times this data structure, and to build this data structure, I need to go through every point and basically hash it. So if it's in d dimensions, then it's going to be like n times d, okay? And then I don't know, you might repeat an extra log n times or something. So it's going to be something like n to the 3 halves, where you need n time to build your data structure once to just dump everything in. Plus you want to do it for many different values of theta. So I'll give you some logarithmic overheads for the multiple values of theta. But then afterwards, you can do lookup in square root n time. So actually, this is maybe actually a wrong way to put it. Let me phrase it like this. This is the construction. This is constructing it or initializing it. And in the query time will be like square root n. And I use this O tilde to hide log factors. Okay. But it's great because you don't have to look at all the points. That's really the goal. Okay. Yeah, and I think in real life, if you're a real sufficiently big company, you'll have somebody kind of watching over and even fine tuning things, and they'll get better than worst case performance, with personal care. Okay, so that's Angular LSH. Uh, so we're going to try to do something similar for Euclidean LSH. Okay, so Euclidean distance. So we can't, it's not angle, so we'll do something a little bit different. I think I left a slide open. Oh, okay. First, I'll mention that we are going to do an approximate kind of thing. So we'll have two parameters. One is sort of the target radius r. That could be like 1 inch or something. And then I have some approximation factor sigma, like 2. So I can either return any point within 2r or declare there's no points less than r. Okay. Here, actually, we're going to let sigma be a parameter, and you'll get bounds if you wanted 1.1 or 1.3 and things like this. Okay, so here's the fun part. Oh, okay, actually, let me, and uh, it's the same up to scaling, so I'm going to assume the radius that we're going for is 1. That'll ease our notation a little bit. That's the only point being made here. Okay. All right, any ideas for coming up with some kind of hashing scheme in Euclidean, high dimensional Euclidean space? Yeah. If you wanted to change the metric, well, sorry, what did you mean maximum? Like coordinate-wise maximum? Uh, that's called L infinity norm, I guess. Uh, uh, okay. Is that a two approximation? So if a I don't know. So take the origin and compared it to a unit vector where in n dimensions it's 1 over square root n everywhere. So the L infinity norm is 1 over square root n, or distance, but the Euclidean distance is 1. So you're off by a factor square root n. That might be tight. That might be the worst case. Okay, so I can try to do, this came up last time too, right? Can I do dimensionality reduction? But remember, we proved something for log n dimensions. And then if I build a quad tree after that, then I'm going to do something exponential in log n, which will get me back, once it's worse than n time for a query, you might as well compare all the points, right? So you don't want to do 2 to the log n. Okay, I can make a hyperplane, so that'll project it onto n minus 1. So if we did something last time, our LSH is going to depend on the angular distance between 2 points relative to the origin. Which now we're looking for something different. If if uh, if I have 2 points that coming from the origin are roughly the same angle, but the distance is very, very far, right? I don't necessarily need those to hash together, even though the angles are the same. So it's a little different. Okay, so I can try picking a random lines through the origin. Um, so, okay, this is sort of complicated. But yeah, you can try picking a random line. I think it's topologically impossible for my fingers to do this correctly because they have to spin around each other. At some point, I have to spin my body. Okay, but you can pick a random line, right? Uh, and then you can project everything onto this line. So projection means I'm going to find the closest point, right? So it's going to be like this, right? So we can compute the projections. You don't need to watch me draw all the pictures, so I'll only do a few. Uh, where I map each point to the nearest point in my one-dimensional subspace, which is a line. Y, and like this. Oh, I'm really struggling, sorry. Okay, so you get the idea. So I can project everything onto the line. And then what? Now I have everything on a line. Oh, I can try to build a quad tree over this or something. I mean, a binary tree. Uh, or, yeah, so binary tree is kind of like binary search. That might kind of work, but I was hoping to try to get something like a hash code. So I am now at least taking many coordinates down to one. So, okay, so remember, my goal is to sort of build a hash table, right? So one of those red points needs to be assigned a hash code of some kind. So when you say nearest or minimum, what does that mean? So I'm just pre-processing the input. There's not even a query right now, right? Okay, okay. So I think that's sort of similar. Can I just build a one-dimensional data structure over this? Um, okay, so for that, well, first our goal is to make a table or a hash, but you'll need to argue that for one of your projections, a good point is going to be the closest point to your query. So for example, in projections, many points are going to get mapped to distance very close to zero. That doesn't look like it in 2D, but okay. Suppose I force you to make a hash code though, because that's all I'm prepared to do. Yeah. Okay, we can try bucketing. So, oh, okay, you can see the word. Okay, that was supposed to be a little more hidden. Okay, I don't know if that gave it away. Okay, oh well. So we're gonna do something like this, where we'll choose a random line and we'll do the projection, and to finally assign a hash code, I might do like a unit interval, okay, along the line, but I'm gonna randomly translate it like this, okay? So I'll randomly shift it, and then those will be the buckets. Intuitively, that's not so different than trying to do binary search, but it's a little different. Okay, so this will be like uh, this could be like bucket 0, bucket 1, bucket 2, bucket 3, bucket 4, and so forth. Bucket -1, -2. We're able to assign a numerical value this way. Okay, and then we could repeat and do that many times and things like this. So that's what we'll study. Okay. Um, yeah. So notationally, it's going to be convenient for us to just sample a random Gaussian vector. It's probably very close to a unit direction. That's what we learned. And then I'm going to sample this alpha, which represents the shift between 0 and 1 uniformly at random. Okay, so I'm taking x and I'm projecting it onto g, so g dot product x, and I'm adding alpha and I'm rounding down to the nearest integer. And that would give a code, an integer code. Okay, so that's what we're going to study. Okay. Any questions about the algorithm? Oh, well, at least the scheme. We still will need to figure out, oh, what are the odds of success? Should I use many codes, many of these projections for one overall hash code? And after that, should I repeat the whole thing over and over again and amplify it? Those things we still need to work out. But the primitive is going to be this. Okay. All right. So let's see here. So at the end of the day, we want to analyze what's the probability that 2 points collide, right? And so I've broken it down into two steps. Where the first step we're going to do conditional on the Gaussian vector g, and then just focus on the shift alpha. And then afterwards we'll figure out how to deal with g. Okay, so this is sort of like a one-dimensional case. If it was one-dimensional, you wouldn't have to do the projection at all, and now you're just shifting a unit interval, right? Okay, so how? Sorry. Yeah. So I think of like unit intervals all the way down, and then the affine shift alpha is going to be between 0 and 1. So just to be, alpha refers specifically, if you wanted to take this intuitive geometric idea and write it down as a math formula, that alpha is that second term plus alpha, and so that's kind of sliding the walls of the interval. Yes. Yeah. So that'll be helpful. You could ask, oh, why not just project and then just do 0 to 1, 1 to 2, 2 to 3. Um, and I guess even in one dimension, right? I mean, you want some randomness because even in one dimension, if I had points at 0.9999 and 1.0001, if you did a deterministic thing and it was always there, you'd always be splitting them up and that wouldn't be good. So you want this. Translation. Okay, so all right, here's that claim. So conditional on G, the probability of them being split is 0 or 1 minus their distance on that line, right? So if their distance is bigger than 1 on that line, then 1 minus the distance becomes negative. But of course, if they're more than 1 apart, then it should be 0, right? Like, because they'll never be in the same interval. So that's good. Um, so yeah, why is this claim true? So yeah, so let's say this is already on G. The distance between them will be this dot product. Yeah. Yeah. Right. Okay. So the whole thing is shift invariant at some level because alpha is going to be chosen randomly anyway. So you could imagine, somewhere around here is 0. I can, for convenience, just draw it at x. Okay. And so it's going to be choosing some value between 0 and 1 is going to be ultimately, will be our shift alpha, right? And if alpha comes in between, or if the alpha puts the line in between, they'll get split up. And if it doesn't, right? So there's going to be some random wall somewhere in this interval. And so this x minus y over g is just representing, yeah, the distance between them. So as long as you're not in that subinterval, you're okay. Could do it more slowly, but that's all it is. Okay, so so that brings us to our next lemma, which is what we really want. What is the probability that x and y um, are going to hash to the same bucket? And so this lemma says that if I let f be the density function of the Gaussian distribution, so that's something like, f of t is like 1 over square root 2 pi e to the negative t squared over 2, this kind of thing. Then the probability that these two collide is going to be 2 over the distance times the integral of 1 minus t times f of t over norm x minus y. I guess I need a dt here. Okay, so It's not obvious, one has to actually check this, but this is actually decreasing in the distance between x and y, which is sort of intuitively what we want. Okay, so how do we show this? Um, well, so first we observed that the projection, as covered last class, is going to be distributed like a Gaussian, where the variance is uh, x minus y distance squared. Okay, so that tells us that in terms of distribution, it's going to be uh, the density will be 1 over the distance times the density of t divided by the distance. And then we just start plugging in. So so the probability that x is h and x hashes to the same spot as y is going to be this integral. So what we're doing here is we're conditioning. Actually, there's a typo here. It should be absolute value. We're conditioning on the projection being length exactly equal to t in absolute value. And meanwhile, here's sort of the density, so not exactly, but sort of like the probability that gx minus y is equal to t norm x minus y. But there's this factor of 2 because of this absolute value, because it could be negative 2 or negative t or t, and it's symmetric. So that's just plugging in the density and doing the conditional thing, and then we plug in the lemma from last time, where this, as we pointed out, is 1 minus t for the values of t between 0 and 1, which means actually this integral, this can change and just be an integral from 0 to 1. So that's it. So nothing too deep, just kind of plugging in and doing some calculations. So okay, so we have this sort of messy, it's kind of closed form, but it's still kind of messy. There's some messiness hidden under the f. So amazingly, what we're going to do is we're not really going to probe too much further at this point. So again, I pointed out that this collision probability, which to this point is exact, so that's nice, is actually decreasing in the distance. That's what we want. And so what we really want to know is, okay, if, again, remember that we have normalized it, so the definition of a near neighbor is distance 1. I want things to collide when a distance is at most 1. And the worst case is when a distance is exactly 1. So whatever that probability is, I'm going to call it p. Okay, so I'm going to let p be this integral for distance 1. Okay? And then I want to compare that to the probability of colliding for things that are not considered close. So things where the distance is at least sigma, where sigma is this approximation factor. So for us, the worst case, we want this probability to high. So it is smallest when when a distance is exactly that approximation factor. So that will give us this integral. And we're just going to call these P and Q from now on. Okay. And now look. Okay, so here's sort of what the algorithm is going to be. We sort of kind of recapped this before, but in the pre-processing step, we're going to take all the points and hash them out. Okay, so we'll group all the points based on their hash code, their locality-sensitive hash code. And then when I'm querying a point y, I'm going to hash y and I'm going to check all the points with the same hash code. All right, so simple algorithm, just like before. And the question is, what are the performance? So, one sec, did I erase something? Yeah. So the probability of one kind of hash succeeding, well, that's p, right? So the distance at most 1, we're going to find it with probability p. And the time we spend in expectation, well, I'm going to pay a constant for the hash. Then every other element may collide with probability p, right? So all these bad noisy elements, they may all, sorry, I said p, I meant q. they're each going to collide with probability q. So maybe I should mention that, in the query step, if you do find a point that's distance less than sigma, you can just terminate right away. So, right, so that's the expected amount of time. Now, to actually find a near neighbor, I'm going to have to repeat many times. So if I want a constant probability of success, then I'm going to have to repeat 1 over p times. Now my running time looks something like 1 over p plus q over p times n. Okay, so this turns out to not quite be good enough for us, but still, I think maybe it highlights, what we're really focusing in on is this ratio, the ratio of colliding versus of bad collisions versus good collisions. So, okay, what we're going to do then to make things a little bit better is we're going to amplify. So here we have k coordinates for some parameter k we're going to choose, and now I'm going to compute k hash codes in the exact same fashion independently. So we have the same integral as before, but now it's raised to the kth power. So now, what is the probability that 2 points collide when their distance at most 1? It used to be p, but now that we have k coordinates, it's p to the k. On the other hand, what are the odds that they collide when a distance at least sigma, when it's one of these bad pairs? Well, this is at most q to the k. So we just kind of ramp this up. But the key thing is that the ratio p over q is getting better. So, okay. All right, so now I've amplified this with k coordinates. And as we mentioned, the probability of success is now p to the k, so that's actually worse, right? So the odds of actually getting the collision we want has gone down. On the other hand, the running time also, uh, the running time also gets better because q to the k, we're basically improving the odds. We're kind of much more aggressively filtering with each additional coordinate. So, okay. So you put that all together for constant probability of success, I need to repeat 1 over pk times. So now I'm getting something like 1 over p to the k plus q over p to the kn time. Okay, so this thing is getting better. Okay, so right. So what did I have in mind here? Okay, so this is, I think, the same calculation. Okay, so that's really our overall running time. Right. So, okay, so if I kind of keep working through this, then we get 1 over p to the k times k plus q to the k n, okay? And right. Oh, sorry. So I should mention that this k is just from computing k hash codes. So, okay, so you have this running time, and the question now is how to choose k. So what we're going to do is we're going to choose k so that k is equal to log n over log 1 over q, so that this term basically becomes 1. So we do that, we plug this in, and overall, the bottleneck becomes this term, and we'll get something like this, log n over log 1 over q times n to the rho sigma, where rho sigma is this ratio between p and q. Okay, so yeah, that's the idea. Looks like the same slide again. And believe it or not, that's actually where we leave it. So So for a fixed value of sigma, we sort of have this, exact P and Q, and then we're going to get dn to the rho sigma, where rho sigma is this ratio of P and Q. And you might say, okay, but that's very unsatisfying. Why don't we actually like analyze this further and get some closed form solution? Well, I've tried and I've made mistakes on this before. It's actually not so easy. But what you can do instead is you can just directly plot this. All right, so I plotted this in Python or something, and you can see that like for a 2 approximate neighbor, you're going to get something that looks like, I don't know exactly, it looks like n to the 0.61 time or something for a 2 approximate neighbor. So the real point is that you're getting some kind of sublinear running time, and this is often a very good trade-off in practice. Okay, so that's it for LSH, and next time we'll try something not completely different. We'll try something different, sort of building on some of this metrics idea, but next time we'll be doing something called L1 metric embeddings. Okay, thank you.